What I'm going to present is not just my work, it's the work that we have done with, and Peter was involved as well, with the Scientific Council, the International Scientific Council of ENGIE, under the leadership of Jan Mertens, who will also be joining us for the panel discussion this afternoon, and who is the Chief Scientific Officer or the Chief Science Officer of ENGIE. And it shows that, so as a scientific council, we are 10 academics, fully independent, so which means that we are free to express our thoughts. And I must admit that ENGIE is very open because we can also make publications out of our work. And that's why I'm so happy that the publication on this symbiosis was just published a couple of weeks ago. It's an open access iScience publication, so you get it for free as part of this conference materials. So chemistry and energy, a symbiotic relationship for a fossil-free future. But before moving into some of the elements showing why they are so interconnected and why they have to be so interconnected, I think it's also, from a European perspective, interesting today to set the broader scene. And I'm really a supporter of the reports by Enrico Letta and Mario Draghi. And when you read those reports, I think there is some reason for concern, definitely reason for concern. If we look at gross domestic product and evolution of gross domestic product, we see that Europe has consistently been dropping and running behind both US and China. Actually, in one of the slides, it's mentioned, so you will find it there. But Jamie Dimon is the iconic banker of bankers. He's the CEO of JP Morgan, the best performing bank in the world, although we also have a best performing bank here, definitely. But best performing bank in the world. And Jamie Dimon was here in July. And he made a speech for the financial world. And in that speech, he said, well, if we look at the gross domestic product of Europe versus the gross domestic product of the US, 15 years ago, Europe was 95% of the US. Today, Europe is 65% of the US. When the CEO of JP Morgan gives such a message, he then concludes with the words, "You're losing." So this means that we have some catch-up to do. And of course, there is another elephant in the room, which is called China. China, which also has made, and I come back to that in a moment, enormous progress, not just in scaling and producing, but also in a real Darwinian competition that kills the rest of the world. Not always fair, but it's there. And last but not least, China is really starting to lead the world in quite a number of critical technologies. This is also what the Draghi report shows. And for instance, if you look at lithium-ion battery storage, you all remember the power outage in Spain a couple of months ago. It's interesting to realize that in Spain, we have a very high level of renewable energy, solar energy, about somewhat more than 30 gigawatt installed capacity, but we have 30 megawatt installed storage capacity. And if you want a balanced grid, and energy will be extremely important for the chemical sector as well, if you want a balanced grid, then you need that battery storage or storage in general to be much more relevant, important, present. And if you then see how China is leading the way in electrification, in grid development, and for instance, battery storage, it's quite frightening if you compare this to Europe. Definitely also because the Spanish power outage was also a signal that the European grid is not so well connected, that it should be much better connected than it is today. Energy, chemistry, that's where energy and chemistry will have to find one another, because if you have to electrify, I come back to that in a moment, if you have to electrify, you have to be sure that you get the electric power you need. So that's a challenge, and that's not the US, that's China. Also critical technologies. If you just look at Mario Draghi's report, you will see that in almost all clean technologies, China is leading the way today. China is over half of the world's patent portfolio in terms of clean technologies. And there was a Russian economist, Nikolai Kondratyev, and Kondratyev is the economist who developed the concept of long waves in economic development. They're called the Kondratyev waves. And those Kondratyev waves have been picked up by people like Joseph Schumpeter, the father of the creative destruction concept, and later on by people like Philippe Aghion, like John Howitt and Joel Mokyr, Nobel Prize winners economy this year. And they come to the conclusion that if you look at the long-term economic developments, you have those waves that are driven by technology over 40, 50-year cycles. The first wave, beginning of the industrial era, was the steam engine. Then came steel, railroads, etc. And if you look at the blocks in the world that dominate economically, they have all been at the origins of such a Kondratyev wave. For instance, when it comes to steam engine, UK and later Europe were at the origins of that Kondratyev cycle. When we talk another one, electricity and chemicals, Europe and also the States, but first and foremost Europe, were leading the way. If we look at what economists predict in terms of the next Kondratyev cycle, they predict, given technology development, given publication output, given patents, they predict that it will be clean technologies. And if this would be true, we will see this within 10 years, 15 years, 20 years. If this becomes true, then it means that the country that will have the most heavy technological foundation on which to build this Kondratyev wave and the economics that follow from it will be China. So that's something for us to really take care of, to really understand, and to make sure that Europe, where we have a solid technology base, that we translate that technology base much faster, much better, much more efficient into industrial scale activities. And I come back to that in a moment, than we do today. And of course, I already made a remark, we will have to look at energy and chemistry in a much more holistic perspective. It's not just about renewable sources of energy, it's also about transmission. And if we want to have a pan-European industry strategy for chemicals, we will need energy, we will need distribution of those activities across Europe, we will need to produce certain intermediates where we have abundance in terms of renewable energy, and then we will have to be able to distribute this across Europe, both in terms of power and in terms of products, intermediates. So this means that transmission and grid development will be another extremely important evolution. And just to give you a last graph on that comparison, this is a chart from Draghi's report. The orange circles, bubbles, are China, the blue ones are Europe, the other ones are the US. Then you see that Europe is still leading. The three at the bottom, Europe is still leading in some clean technology areas, but we're rapidly losing leadership. Think of electric vehicles, think of batteries, think of everything related to solar. And now we see that European industry that has for a long time led the way in wind energy is also under extreme pressure. And as I said, if you just look at this one, this is the number of patents filed on clean technologies, and recently the amount of patents filed by China is more than all the patents filed by all other countries in the world. So this is something to really keep in mind. And this also means, because patents are a result of most often definitely in those technological areas, are a result of scientific research. This is a reason why we need to keep and the science, and the innovation, and the scaling at high intensity, at high levels. It's not just going to higher TRL levels. We need the low TRL levels, and we need the high TRL levels. They're both necessary. One of them alone is necessary, but not sufficient. If we want to have a necessary and sufficient scaling, we need both. And then we see Europe's challenge, and that's one of the last general remarks I want to make. This is a paper that was published recently by the Joint Research Center in Sevilla, one of the research groups of the European Commission, which shows that across the world, this is not just Europe, across the world, the R&D patent elasticity, the elasticity with which R&D gets translated into patent output, is declining tremendously, also in the chemical sector. And the R&D labor productivity, the way in which R&D is translated into economic progress, is also declining across the globe. And the European Commission concludes R&D productivity in terms of patents has been falling globally, but most strongly in the United States and in Europe. Coupled with the European Union's persistent weakness in transforming its R&D into commercially successful product innovations, and the estimated R&D labor productivity elasticity show it, that seems to warrant urgent policy action to bring the EU back on a growth path that secures the long-term global competitiveness. And if we want to unravel those relationships, then definitely the link, the symbiosis, chemistry, energy comes to the forefront. I already mentioned Jamie Dimon, but it's interesting. It's on the website of the European Commission, so everyone can read it. But 1 year after his famous report on European competitiveness, Mario Draghi, the 16th of September, together with President von der Leyen, gave a speech, and he was rather pessimistic. The key words in his speech are, Europe is too slow, Europe is complacent, Europe is not translating and fostering its global competitiveness. And he gives many examples where we are lagging behind. So there is work to be done. And of course, it's not just about productivity. It's not just about the challenges from China. It's also about the fact that Europe and sustainability are intimately linked, and we are on a path towards defossilization as well. And when we look to that path, it means that by end of this century, fossil fuels will definitely mostly be gone. But still today, and that's where the chemical sector is really in a conundrum, we have fossil fuels that we need as a feedstock and as an energy vector, but we need to get rid of them. And the way we have to do it is something that will call for the necessary pragmatic approaches. People are looking to China, and there is this interesting publication last week by Bruegel. Bruegel is a European economic think tank, and I advise you, it's available on their website. I advise you to download the paper and have a look at it, because it's a very interesting analysis as to how, on the one hand, China is electrifying at rapid pace, and on the other hand, they're still opening new coal-fired power plants to get the electricity they need to electrify. So it's kind of a circular reasoning where China is setting up a completely different path than Europe is doing, but at the same time, you see that they are, in the end, electrifying and developing a technology base at a very, very high speed, so we have to be aware of that. And this means that by 2050, 2060, fossil will have decreased a lot. And I'm always, I would say, a bit reluctant when there is too much alarmism. If you look at what Dat Norske Veritas, which is one of the premier European engineering firms, engineering consultancies produced also a couple of weeks ago, then we are still in the bandwidth 1.5, 2 degrees global warming is still feasible. So this means that if you look at the latest outputs from engineering offices, agencies like this one, it's not that everything is lost, on the contrary. But of course, we will have to make the right decisions. And for the chemical industry, the right decisions also mean that we have to think electrons and molecules. And there has been a lot of work done in the area on, for instance, hydrogen. And more we come to the conclusion that hydrogen having a very low energy density and being hard and expensive to store and to move around is something that we should develop and use, but maybe not at the scale it was predicted that we should do it in a short-term time frame, because that's something which is at odds with what we experience today, both in development, infrastructure, transport, and use. So energy vectors will have to be considered carefully, will have to be deployed carefully. And Peter was referring to methanol. We have methanol, ammonia, and other carriers that may become much more important in the near future. So understanding transition also means understanding limitations and right-sizing our policies, because there can be many billions of euros in lost investments if we don't choose the right targets. And that's, once again, where the energy sector and the chemical sector meet one another, can reinforce one another, can have a lot of bandwidth together. Now, turning from that general picture to the more focused one on the chemical industry, it was already mentioned, the European chemical industry is under pressure. If you look at the EBITDA, the earnings before interest, depreciations, and amortizations of chemical companies, there is only one trend you see, and that's a downward trend. EBITDA is decreasing. And if you look at major players like BASF, for instance, you see that they are really under pressure. And the nice thing about those companies is they have become very efficient. But in the energy transition, coupled to the feedstock transition, are they still on an effective pathway? Efficiency versus effectiveness. That's the big challenge. And you see that definitely in Europe. This is another graph from the Draghi report. You see that alongside the Chinese competition, there also is an energy price gap, energy price challenge, both at the level of gas and at the level of electricity that is important, that is really important and significant. So this means that our chemical companies that were once kind of a crown jewel of European industry and European industry policy are under pressure from various perspectives, from various angles. And that's, of course, something that is more than worrying. And if you look at the main basic chemicals that we need in many products, in many applications, ammonia, methanol, ethylene, you see that all of them have a very high energy need in order to bring them forward. And so it's really a no-brainer to say that without energy, you will not do the transformation of the chemical sector, and the transformation of the chemical sector will not happen without the transformation of the energy sector. And if you then look globally, it means that in terms of gigatons CO2, chemicals is 4% of the 37 gigatons CO2 that was emitted in 2022. And those chemicals, if you just look at the breakdown, about 2/3 of it comes from ammonia, ethylene, and methanol production. And what's also interesting and relevant, and that's an important link to the feedstock issue, this is an integrated, what we call scope 1, 2, and 3 picture, because about 2/3 of the emissions are incorporated carbon in the products that the chemical industry brings to market. About 1/3 1.3 gigatons is what is used in process and energy emissions. In producing the products, about 2/3 is inside the products. And this, of course, means that from a feedstock perspective, the products that are generated by the chemical industry can be turned into feedstock again, sustainable carbon, because whether we like it or not, well, it's not whether we like it or not, it's just a physical reality, carbon will always be around. No chemical industry without carbon. Carbon is an absolute necessity for the chemical industry. What does this mean? It means that a sustainable chemical industry will need sustainable carbon feedstocks. And that's the work that we have done over the last year. Then, of course, we have to understand what are sustainable carbon feedstocks. We summarize them into 3 main categories. One category is biomass, a second category is recycled plastics, and a third one is CO2. And it's obvious that scaling the technologies we need for that sustainable carbon feedstock is an important pathway, is an important journey for transition of the chemical industry. And, of course, for those of you who saw the video before entering the room, it's obvious that this is at the heart of what Catalisti is doing. Catalisti is looking not only into energy, but also into CO2 and definitely into sustainable carbon feedstock for the chemical industry. And another important element, when we talk symbiosis, energy, chemistry, we should not forget that we will enter into competition with other applications as well. And one of the major other application areas where we will enter into competition, for instance, when it's about biomass, will be the agricultural sector, will be sectors like pulp and paper, will be wood construction, etc. So this means that if we focus on the 3, there are many challenges, technological challenges, scaling, higher TRL levels, higher intensities, but also competition with and prioritization with other applications. So when we look at biomass, as I just mentioned, these are different sectors that will come into competition, into the arena when looking at the chemical industry in terms of feedstock. Recycled plastics is something which we can expect to become a major pillar. Okay, sorry, I was pushing the wrong button. It's something which is a major pillar when we want to look at sustainable carbon, but today only 10% of plastics are recycled globally, and we expect this to increase to 45% by 2050. But also there will be another elephant in the room. I was still yesterday talking to a number of people from European industry, and they told me, look, if you want to do plastic recycling, you have to understand that in 27 European countries, there are 27 different regulations when you do this recycling step up. So that's another area where Europe will have to tackle. How do we make sure that we bring this to a much more easy, transparent regulatory environment? And that's why I'm also looking forward to what the European Commission is trying to come up with these days, called the 28 regime. How are we going to make sure that we can have unified regulatory or legislation standards across Europe without all the gold plating and all the fragmentation between 27 countries? And for recycled plastics, this will be highly necessary. And then, of course, there is an abundant source of feedstock, only we have to capture it. It's called CO2. Because CO2 is not just an emission we have to get rid of, it's a feedstock, it's a resource. So we also did some work on that in the past, but CO2 as a feedstock means that we have to capture it. Luckily, there is work being done also in the area of Catalisti on carbon capture, carbon storage, carbon utilization, but also direct air capture is something that will have to be investigate, well, it's not investigated, it's being developed, but will have to be developed at a much more economic level than we have it available today. We really have to go below 100 euros per gigaton for it to become competitive. Where is Europe? Well, if I just look at some groups and colleagues, some of them here in the room, then there is a lot of work being done. Bert Weckhuizen in Utrecht, who has quite some connections with colleagues in Ghent and in Leuven and other Flemish universities. Bert is thinking about the refinery of the future. What will the refinery of the future look like? And in the process models that he has developed, you see the different feedstocks, CO2, biomass, recycled plastics, that are fed into the refinery of the future. But it's a huge challenge. If you read his paper, published in Nature last year, if you read his paper, we have globally 615 refineries that will have to make that transition. He counts that in order for the 615 refineries to make the transition, we will need an annual investment between 320 and 520 billion euros till 2050. Yeah. So 25 years, let's take the midpoint, 25 years, 420 billion euros of investment. This is huge. This is simply huge. And it's not just the investment for the transformation and the transition, it's also making sure that the electricity supply will be up to level. In the neighborhood of Antwerp, let's say 300 kilometers around Antwerp, there are like 40, 50 steam crackers. If you electrify each steam cracker, you will need an installed capacity of about 0.81 gigawatt electric, which is an enormous investment in power and also an enormous need for transmitting that power. And then, of course, the skeptical person that I sometimes am says, well, if you see what it takes to get one Ventilus done, we will not need one Ventilus to do this, but we will need 10, 15, 20 to do this. So a lot of work ahead. But science has answers. That's what this is showing. Another group working closely with and deeply involved with Catalisti, the people who are working on lignin, Vito, the group of my colleague Bert Sels, they have also published quite some work and done quite some work as to how hydrocarbons, oxygenates can be used, introducing also low-carbon hydrogen, because that's something we have to be aware of, low-carbon hydrogen, introducing and injecting it into the process to make sustainable hydrocarbons. So also wood and is a source of renewable carbon, and also there, here the colleagues of Catalisti do a lot of work. And it's important to mention hydrogen will be important in such a process, but if you look at the Clean Industry Act of the European Commission, you will see a subtle change over the last 1.5 years, and that subtle change mentions, well, it's not just green hydrogen, it's also low-carbon hydrogen. If we can work with low-carbon hydrogen, then all of a sudden a lot of possibilities open up, because if it all has to be green hydrogen, then we run out of the necessary electricity to do so. But also the question is this the most efficient way of using our electricity that needs to be used for so many other purposes? But wood, biomass as a source gives us interesting pathways towards products, chemical products as well. And of course, there are many technologies available and many applications when you look into biomass. This is just a recent report looking into different application areas, different types of biomass, biocoal, used cooking oil, UCO, municipal solid waste. All those different sources can be used in order to make sure that we create the feedstock of the future. And there is one red column here, and I think that's something we are all pushing for. Is it competitive with unabated approaches? The answer is no. But is it competitive when you compare it to other net zero approaches? Then the answer is yes. And in the last column, you see what scalability is. And that's really also, and I do hope we are moving into that direction, that's really where the fiscal support for fossil will need to transform, to translate, or to switch towards support for electricity and renewable electricity, because that will make those different technologies competitive. But it's not only about the pricing of the fuels, it's also about the fact that we need circularity. This was a paper that just published, just appeared by the Energy Transition Commission. And if we look at carbon demand for chemical industry, and if we introduce, I have to see that I push the right button, if we introduce full circularity in our value chains, then the prediction is that circularity levers could reduce 30% of the primary carbon demand by mid-century. So circular economy will also gain a lot of importance. And in the link, in the nexus between, on the one hand, energy, on the other hand, chemistry, circularity will have to fill a gap. And this means also understanding how we organize such a circular economy when it comes to, for instance, everything related to the carbon demand for our chemical industry. As I said, biomass, recycling, because circularity will also be about recycling, and finally CO2 capture. And there we see that there are different predictions, and that's the volatility we face, the risk we face going forward. And the risk we face going forward is about what will direct air capture do. Will it become cost competitive, or will it still take 10 years, 15 years, 20 years before it becomes cost competitive? And if you just look at the International Energy Agency, if you look at the Energy Transition Commission, you see that their estimations of the impact of DAC are really varying a lot. If you also look at the price range that is predicted of direct air capture going forward, we are at multiple hundreds of euros in spreads on in different reports. So this means that technology development, we know how to do it. Climeworks in Iceland is a nice example of direct air capture, but we also know that there are challenges in cost effectiveness, that there are challenges in scaling, and that's, of course, given the pressures our chemical industry is facing, that's something that needs to be resolved. Another thing which is interesting to realize is that the bulk of scientific publications today in the area of direct air capture does not any longer come from Europe or the US, but comes from China. So meaning that in China there is a lot of development going on in the area of direct air capture, going back to my earlier, let's call it fear, that we may underestimate the leadership that comes from that part of the world in terms of clean energy, clean technology. So this is another paper that we published last year, where we looked at evaluating different carbon removal technologies. Also, this paper is available on the web, on the CellPress website. It's also open access, so you can download it for free. But here you see for the different carbon removal technologies, and this is just, I always keep pushing the wrong button. For the different, and this is one table out of 3 or 4 tables, you see that TRL levels are gearing up, but still have a way to go. Direct air carbon capture and sequestration is at about 7. The potential by 2050 can be estimated at 110 gigaton CO2 per year. That would be an enormous amount if we could accomplish this. But the price range, the cost predicted by 2030, in terms of piloting and first results, you see between 100 and 600 euro per ton CO2. That's really not economically viable at the moment. And it's not just that it's not economically viable, it also shows how broad the range is. So in other words, there is a lot of technology work, technology optimization work, and further development work to be done. But that's when we look at feedstock. We also need energy, because chemistry is about feedstock and is about electricity, of course, or is about energy. Of course, all of you know this, but this also means that we have to move towards electric heating technologies, probably because heat is an important factor in the chemical industry. Heat pumps today, high-temperature heat pumps, can go to 180, 200 degrees Celsius, but we need higher temperatures in the chemical industry. We need 2,000, even 3,000 degrees Celsius. And there we see that technologies like as induction heating, resistance, plasma torches, electric arc furnaces are reaching higher TRL values today, but still have to be developed further. And just to give you an impression from a different sector, but a closely related sector, when I talk to people at Arcelor in Ghent, they're also confronted, just like the chemical industry. Steel industry is confronted with similar challenges. A blast furnace, electrification of a blast furnace compared to a traditional blast furnace is a capex difference between 250 million euros to build a traditional furnace versus 2.5 billion euros to build an electric blast furnace. So it's capex, and then you still need the electricity at sufficiently cheap prices to operate it. So the challenge is huge, but as an energy vector, if we want to become fossil-free, it means that the chemical sector will have to turn towards electrification, and this means sufficient capacity and a reasonable pricing, both OPEX and CAPEX. So the challenge is huge. If we then look at, and I already highlighted this, but in some more detail, if we look at biomass, the challenge with biomass is that inherently it is hydrogen lean and oxygen rich, but most chemical products are hydrogen rich. So this means that once we want to do that biomass conversion, we will need hydrogen to make sure that we have a better yield in our biomass to chemical processes. We need to substantially increase that yield, and this is where low carbon hydrogen will come in, and we will have to take this into account. Another step or another angle from which to look at the chemistry energy transition has to do with biogas and biomethane. Also two important elements, two important stepstones for more sustainable carbon development. And there is an intermediate step there, which is the step towards syngas, CO plus H2. And that syngas can be produced, can be used then in Fischer-Tropsch processes, but the most relevant or the most frequently used process today is steam methane reforming, but colleagues in Ghent are working very diligently on what we call dry and super dry methane reforming, which would be a real breakthrough if this can be scaled towards the higher levels, TRL levels, as compared to what we have today. So this means, once again, novel processes to produce sustainable chemicals to make sure that we arrive at the carbon we need in those processes. And there is another element that we will have to take into account, and that's really pan-European. That's logistics, location, relocation. What will we do? For instance, when you look into biomethane, will you produce it where you have abundant renewables? Will you then transport it by grid the gas transport grid to the chemical plant, or will you transport biomass to the chemical plant and use it there as a feedstock? So this means that there is a tremendous supply chain, value chain challenge across Europe. And that's what I mean when talking about pan-European perspectives. Are we willing in Europe to consider a logistic redistribution of, for instance, our chemical sector, where certain intermediates will be produced in areas with abundant renewable energy, and where then there will be value-added activities in other locations in Europe? This means a reconfiguration of the value chains in Europe, where energy transmission, and configuration of our chemical plants will be at the cornerstone. And for me, that's almost a binary decision. If Europe and European chemical groups and energy groups and the European Commission do not succeed in developing a real effectiveness-driven vision on that distribution, location, relocation, energy distribution, intermediate distribution, then I fear that the violence and the violent attacks that we see from Chinese companies in those areas will just increase, go on, and will in the end be to the detriment of our own chemical sector. In our paper, so the logistics value chain configuration is something to take home and to think about. And I do think that also when we look at all the marvelous Catalisti projects and basic research projects in scaling, we also need to understand how will the value chain scale alongside the scaling. That's a lesson and a challenge to take into account. Feedstock and energy, those are various technologies. I mentioned a few of them, but you see the time horizon is still 2025 today. We definitely think that it will take till 2045 before a number of them will be really at high enough TRL levels and scalable. Some of them are in pilot phase today. Some of them will only get into pilot phase within 5 years. So there is a lot of work to be done for Catalisti and the Catalisti teams from that perspective. But at the same time, we should understand that our chemical industry will need support in order to get from here to there, because that's a long time frame. That much is sure. So this means that what are a number of important recommendations that we can make in terms of convergence towards a fossil-free future? Well, electrification. Electrification will be key to defossilize the chemical sector, that's for sure. But that means abundant renewable electricity, that means grid capacity, and that means that we will also have to look into import of intermediates from energy-rich regions. Second point, the role of hydrogen. Definitely low-carbon hydrogen will be important in terms of sustainable carbon production. And finally, what about direct air capture? Well, as I mentioned, this is a long-term carbon supply solution, but it's not there in the short term, so we will have to look at other technologies. And we're not the only ones coming to those conclusions. Also, the Energy Transition Commission came to that conclusion in a report that was published like 2 weeks ago with 8 main lessons. I'm not going to read them all. You can read them in the presentation that will be shared. But you also see an overview of the different technologies and the cost predictions to introduce those technologies. And some of them will be more feasible in a short time frame than others. So also this is something that you really have to take into account. And this brings me to some concluding remarks. Concluding remarks on a paper that was published by my colleague Ronnie Belmans together with Jean-Marie Glachan, and they looked into pan-European value chains. And I do think, as I mentioned, this is something that we should never forget. Pan-European value chains that are about electrification and that are about clean molecules, and they go hand in hand, and they have like 5 constraints that Europe should handle. Electrification is equivalent to energy efficiency first. Defossilizing is the motto. Clean electricity requires a lot of investments and gigantic transmission investments. Clean electricity also requires the creation of a new integrated industry. And the chemical sector, chemical companies are part of that integrated industry. You definitely need clean molecules. And finally, we have to make sure that those clean industries, even if they are energy intensive, are still welcome in Europe. And welcome in Europe means pricing, making sure that electricity is affordable for those companies, but it also means regulation, making sure that we stimulate and we do not suffocate innovation, because there will be a lot of product innovation needed. So this means that we have to rethink the energy chemistry nexus, and there are 3 lessons there where we see and where we highlight the complementarity between the different technologies and the different approaches that I just mentioned. We will have to reconfigure the chemistry energy value chains. What will be done in what location of the world? And let me rephrase it, in what location in Europe? What will we do in Spain? Spain is an ideal region for solar technology, for solar energy. We can do a lot there from a chemical perspective as well. So this means that the value chain configurations will change. Conserving today's production patterns by shipping hydrogen is substantially costlier, whereas trading intermediate products could save costs while keeping substantial value creation in renewable, scarce importing regions. So there is a future, but this future has to really be capitalized on and has to be really well focused. And that means no journeys like, for instance, some of the hydrogen journeys that we have seen, no journeys on their own. It really needs to be integrated in a chemistry energy policy. And I want to conclude, I'm going over time now, I want to conclude with a number of remarks. In Europe, we can look back, and we have that very nice book by Stefan Zweig that was published in the 30s last century, Die Welt von Gestern. We can be nostalgic about what we were 10 years, 20 years, 30 years ago. But I do think Johan Norberg published a much more interesting book, Peak Human, that was published this year, and where he says, well, actually what we need to do is we need to maintain our societies open. We need to maintain open trade. Rich nations, well-to-do nations, like, for instance, the Dutch Republic in the 17th century, were regions, nations that were open to trade, that were open to talent, that were open to science, that were open to innovation. Let's keep that spirit in Europe, but let's also turn it on scaling those innovations. And I want to conclude with the words of Antonio Gramsci. Gramsci is a Marxist political philosopher. He was imprisoned under Mussolini. But he wrote a very interesting book, The Philosophy of Praxis. And in the philosophy of praxis, the main tenet is you have the pessimism of the intellect, and some of the things that I presented is about the pessimism of the intellect, but you have the optimism of the will. And I do think that if we capture the synergies that I have been referring to, and not just I, other people, colleagues in our council, also colleagues in other institutions are focusing on today, if we have the will to bring those synergies to play, I think there still is, it will be a hard road, that's for sure. It will not be an easy journey, but there definitely is a way forward for both the energy and the chemical sector in Europe. And I do think we have the solutions, we have the brains to do it. And then I come back to what I see each time I'm entering engineering school in Stanford. The only way to do it, just do it. Well, let's just do it. Thank you for your attention.